grade 12 chemistry students. Today what we're learning about is valence bond theory and hybrid orbitals, specifically how to draw orbital overlap diagrams. So as you may recall before, you have different blocks in the periodic table. For example, this is the S block. Over here you have your P block. Sorry, it's right here so you can see it. This is the P block. Here in the middle, the transition metals, this is the D block. And down here is our F block. And they represent a different amount of orbitals or suborbitals, and they have different shapes. For example, the S is a sphere, and the P orbital looks like three dumbbells, the PX, the PY, and the PZ. We're going to focus on the PY and the PZ today. You need to know those shapes. So what is the valence bond theory? Well, what it is a covalent bond is formed when you have two half-filled orbitals overlapping. They share the same space, and they combine to produce a new orbital containing two electrons with the opposite spin. Imagine we had two s orbitals approaching each other, and what they wanted to do is form a covalent bond. Well, what has to happen is they actually have to form a brand new orbital, one in which it's almost like two soap bubbles coming together. They form one new orbital, and they have opposite spins, and that is a covalent bond. So when atoms are in the bond, they arrange themselves to achieve a maximum overlap of their half-filled orbitals to produce an orbital with lower energy. So this one has lower energy than the two separate orbitals. This makes the atoms more stable and less reactive. And again, the octet rule still applies here. So when you have two orbitals that overlap end to end, they just touch ends, we call that a special type of bond. It's called a sigma bond, okay? And sigma bonds occur, like for example in H2, the Lewis structure for H2 is just this. Recall that hydrogen has 1s1. If we were going to do the energy level diagram, this would be 1s1 for both of these guys. And you would have two of them, so you'd have one electron in each. And overall, they would overlap and form a brand new orbital, and it would be called a sigma bond. So this would be a sigma bond between these. We also have F2. Let me show you the energy level diagram for F2. So this is the energy level diagram for fluorine right here. It's 1s2, 2s2, 2p5. And you can see that it has one of these p orbitals, we'll call it the px in this case, that is not bonding, or it doesn't have two electrons in it. It's half filled. So if we were going to draw it, we would draw it like this. We would have our fluorine atom, and then we would have one px. So this is going to represent the px. The other two are full. And I'm going to put an electron in there. And we also have another fluorine since it's F2. And that also has a p orbital. And in there is another electron with the opposite spin. And this is showing two orbital overlap diagrams. Sorry, it's showing two orbitals that are overlapping. And since they're overlapping end to end, we call that a sigma bond. So we'll talk about the other type of bonds later, but that's what it looks like. So next time we're going to take a look at H2O. The Lewis structure for H2O is the following right here. And if we draw a energy level diagram for hydrogen, it's 1s1, and it's going to be 1s1 for both of these guys. And if we draw the energy level diagram for oxygen, it will be the following. Now it's 1s2, 2s2, 2p4. This is for oxygen, and you can see that we have one p orbital that's full, and we have two that are half full. Now I'm going to say the pz is full here, and that's coming out of the board and going into the board. And we're going to say that the py is half full, and we're going to say that the pz is half full. So when we look at this, the following will look like this. Let's draw our oxygen. And so our oxygen has a py that's coming out of it that's half full. And we also have a px that is half full as well. Now there's a pz that is full. We're not going to even draw it because it's completely full and it's not going to be involved in bonding. So this is our py because it would be on a y-axis, and this would be the px because it's on the x-axis. This is the x, this is the y. Now we also have a 1s1 orbital for our hydrogen, so I'm going to draw our hydrogens next. So our hydrogens would look like this. We would draw a s orbital, a circle or a sphere because it's 1s1. And this is our hydrogen, and we will give it an electron with the opposite spin. Now that is called a sigma bond there. It's a sigma bond because these orbitals are overlapping end to end. The same thing will occur with this hydrogen here, which is also 1s1, and it also forms a sigma bond. Now this shows us something unique here because it really describes the shape of water. Water is supposed to be bent, and you can see it's bent in our Lewis structure. Well, it's also bent in our orbital overlap diagram. Recall, I can't take this hydrogen and place it over here because this is part of this orbital that is full. Okay, so you can't have two bonds. So it can't be a linear shape. It has to be bent. This is why the orbital overlap diagram is sort of superior to our Lewis structure. It explains why it is bent. Now there's some very specific problems with this, and one of the problems is with valence bond theory is that it can't explain the four equal bonds of carbon, okay, and which we'll explain in a moment. And it also can't explain the existence of double or triple bonds. So it can't explain why carbon actually has four bonds. It doesn't really explain it very well, and let me show you what it means. And it also can't explain double bonds or triple bonds. So we need something called hybrid orbitals to help us explain that. To help us understand why it can't show us what a double bond is happening, or what also it can't show why it's having four bonds, we need to draw the energy level diagram of carbon. Recall it is 1s2, 2s2, 2p4. So I'm going to write that right now in the energy level diagram. So this is the energy level diagram of carbon, showing you all their orbitals. And how many bonds would you expect carbon to make according to this? If we looked at this, we would see that carbon could only make, oh, sorry, my bad, this is not carbon. Let me fix. I actually showed you oxygen. This is carbon, it's 2p2. And you can see it only can make two bonds here. Carbon's supposed to be able to make four bonds, but clearly you see that it's making just two. So hybrid orbitals allows us to figure out how to make four orbitals that will look exactly the same, have the same energy, and have four orbitals available for bonding. It's also going to show us how double bonds can be made. So hybridization, you can see that I've got 3p orbitals here and one s. It's when two or more different pure orbitals, s, p, d, or f, we're only going to concern ourselves with s and p, can be mixed to yield two or more hybrid orbitals that have the identical shape. For example, for methane. Let's take a look at methane now. This is the Lewis structure for methane, and you expect carbon to be able to make four bonds, but when we look at the energy level diagram, it looks like this. Here it is, and you can see it's only going to make two bonds, but we need to clearly make four bonds. So hybrid orbital says something here. It says that we're going to get something called a promotion. And a promotion will occur between this 2s2 electron and this empty p orbital here. So this electron here gets promoted up to here. And what we're going to see is that we have four available orbitals for bonding. So you can now see with the promotion I have four available orbitals, one s, and three p's that are half filled. So I can now make four bonds. But the issue is that all these bonds we know from experimentation are exactly the same. So that means that one is not an s and three of them are p. Instead, what we say is that they hybridize to form a brand new type of orbital. So what happens is you get four brand new orbitals of equal energy. So these four orbitals come together and they hybridize and they equal out their energy. The energies of the p's decrease and the energy of the s increases slightly, and you get four brand new orbitals all of equal energy. And because three p's went in and one s went in, we call it sp3 hybridization. So you can see that we have 1s and 3p orbitals here. This is what sp3 hybridization looks like. You end up combining these three orbitals and forming brand new orbitals.
It's four equivalent sp3 hybrid.
Okay, so you have 1s and 3p's come together and they form brand new types of orbitals that kind of look like bowling pins now, and they form what we call a tetrahedral shape. And that's got a 109.5 degree angles between it. We'll talk about what that shape looks in 3D in class, but it's a tetrahedral shape and every single orbital is the exact same energy. So to draw this, what we would show is we show our carbon. And then we would show some orbitals going off of it, but we'd have our sp3 orbitals going off our carbon. Now when we draw this, we try and draw them again like bowling pins, okay? And I'm going to show you 4 of them, and I'm going to try and draw them in a tetrahedral three-dimensional shape. So this is my sp3 orbital, and each one is half filled, okay? We take a look at hydrogen. We recall hydrogen is 1s1. It does not need to do any hybridization to do its one bond. And so what we have is we have a hydrogen orbital, a s orbital, with 1 electron in it spinning in the opposite direction. That is what we call a sigma bond. It's end-to-end. And we have that occurring at the end of every other sp3 orbital. Recall there's 4 sp3 orbitals, and there'll be 4 hydrogens around our carbon, so we'll have a 1s1 orbital around each one, making a sigma bond. So this is what our energy orbital overlap diagram looks for CH4. You can see that this is a tetrahedral shape. The angles between all these orbitals will be 109.5 degrees, and it is a stable. All these orbitals are the same way, and so this is how hybrid orbitals solve the problem with carbon making 4 identical bonds. Listen more for another video tomorrow on further hybridization.